Okay, this is on your own 13.6, and again, we're using Hess's law, but this time you have to incorporate stoichiometry to find the amount of energy when you burn something or create something else. So this is 13.6. So it says ethane gas, and it gives it to you, C2H6, has also been considered a fuel for automobiles because, like octane, it releases a lot of energy when it is burned. How many kilojoules of energy are released when 250.0 grams of ethane undergo complete combustion? Okay, because it gives you a phase change, I would use Hess's law immediately right off the bat. So first of all, you have to write the equation. So they gave you this, and they told you you had complete combustion. So you should know that means I have to add oxygen, which is a homonuclear diatomic, and I always get carbon dioxide and water. Don't worry about this for right now. Now I need to balance it. Well, I wanted to show you how I balanced it because I wasn't sure if you remembered this. So when I first balanced it, I said, okay, I've got 2 carbons, so I need 2 carbons. And then I said I've got 6 hydrogens, so I need 3 hydrogens. But then I looked up and tried to balance my oxygens, and I said, well, I've got 4 and 3, that's 7. So when you have something odd like that, if you guys remember, you can put 7 over 2 up here, and you can multiply everything by 2, and when you do that, you're going to get rid of the fraction. So when I multiply this by 2, and I'm going to go ahead and erase it, because I'm going to multiply everything by 2. When I multiply this by 2, I get 2 of these. When I multiply this by 2, I just get 7. When I multiply this by 2, I get 4. And when I multiply this by 2, I get 6. So then if you check it, it should be balanced after that. So let's just check. I've got 4 carbons. I've got 12 hydrogens. I've got 14 oxygens. Let's see, I've got 8 and 6, that's 14. So I know this is balanced. Okay. So once it's balanced, then what you have to do is you have to use table 13.2, and you have to look up the enthalpies for the summation of the products, and then you have to subtract the summation of the reactants. So here's what we do. We say, I've got 4 moles of CO2, so 4 times the enthalpy of formation that they gave me. I'm going to add 6 moles of water. So I multiply 6 times the enthalpy of formation of water, and that's all in a bracket. Those are added together. Then I'm going to subtract out 2 moles, because of my 2 moles here, times the enthalpy of formation of C2H6. And then instead of adding something else, if you guys remember from the module, it says that when you're doing Hess's law, anything elemental, which includes homonuclear diatomics, is always 0 for enthalpy. So that's just 0. So then what I like to do is I like to multiply it out and make it go vertically, because that way I can see where I need to have my need to have my numbers in for significant digits. So I multiplied 4 times this, and I get negative 1576. 6 times this, and I get negative 1452, which I'm adding these, but basically I'm adding negative numbers. Then when I come down here, I'm subtracting a negative. So 2 times 84.7 is 169, and it ends up being positive because when you subtract a negative, it's positive. So my enthalpy, change in enthalpy, is negative 2859, and I have to take it to the units because that is my least significant digit. So here's my number. I know that it's exothermic. This doesn't tell me that it loses or gains energy. It tells me where to place it. Remember Mrs. Tanner called this a locator? I like that. So it tells me that the energy belongs on the product side. So I'm going to put it up here so I remember where it goes. Now you go to the second part of your equation. So they told me I had 250.0 grams of C2H6. Well, I'm going to convert that to moles. So I take my AMUs, moles, and I get 8.31 moles of C2H6. Well, I'm not quite there yet. I take that 8.31 moles of C2H6, and I have my own conversion factor down here that I found out. I found out that when I burn 2 moles of C2H6, when I burn that, then this much energy is a product. So I have this relationship. 2 moles of C2H6 produces this much energy. So I can use that to get rid of moles and to end up with energy what I need. So I multiply this times this, divide it by 2. I'm looking for 1, 2, 3 significant digits. Here's my number. I have to put it in scientific notation in order to show the 3 digits. And I end up getting 1.19 times 10 to the 4th kilojoules of energy. Let me look at my notes really fast. Can you pause it for just a second?
You stop it.